Okay, hello everyone. I'm Depanita. Welcome to the 8th interaction session of Fundamentals of Electrical Engineering. For this week, you have been taught about single phase AC circuit, so we will be solving a few problems of that. So, the first problem that we have here is you have been given a circuit with one AC source and one DC source, voltage source, I mean. It is connected with a resistor, inductor, and capacitor. So, in the question, it is asked that the instantaneous voltage of AC source is given as 5 sine 5t. Now, if this circuit is in steady state, what is the RMS value of current in ampere flowing through the circuit?
Ma'am, your sound is not audible.
Okay, just is it audible now? Uh, can you hear me? Uh, Let me probably use a headphone. Just hold on.
So, is it audible to you now? Sharad, are you able to hear me? Are you able to hear me now?
Yes, ma'am. Now audible.
Okay. Okay, so we were talking about this circuit as shown here. It has one DC voltage source and one AC voltage source, and they are connected in series with a resistance, inductor, and a capacitor. So it is said that if the circuit is in steady state, what is the RMS value of current in ampere flowing through the circuit? So earlier, like just up before this week, we had only looked into a DC source connected with a resistor, capacitor, or inductor or anything else. And at steady state, we had like shown how it is short circuited or capacitor is open circuited and all those. But right now we have both an AC and a DC source. So we have to compute the current separately for the AC and DC in order to get the total RMS value of current under this steady state condition. So here the instantaneous voltage is given as 25 sine 5t, right? So it is in the form of I max, maximum current, sine of omega t. So here 5 is actually omega. So we have omega equal to 5 and I maximum is 25. I maximum is 25. These are the two information we have. Now under steady state condition, to only the DC voltage source, since it is in steady state, it will only face this resistor, right? Rest won't be like resisting this flow of current from this particular DC. So let us just calculate IDC. IDC will be equal to VDC by the resistance, which is 10 by 2.5 ohm. This comes out to be 4 ampere. Okay, now look into the RMS value of it. So uh, the IRMS current that will be flowing will be equal to voltage divided by the total impedance of the circuit. So let us first calculate the total impedance of the circuit, which is given by Z, that is square root of R square plus omega L minus 1 by omega C, right? because we have capacitance and inductance, right? This is minus j by omega c, and this is j omega l. You haven't taught this one, right? So the total impedance of the circuit will be square root of magnitude of the part coming from the inductor and capacitor and the resistor. So this will be equal to R, we have 2.5 whole square. So omega is given as 5, L is 300 millihenry. So basically it is 300 into 10 to the power minus 3. Minus 1 by omega is again 5, C is 100 millifarad. So 100 into 10 to the power minus 3. This one's not a whole square. So if you just compute this, this is 2.5 square plus this whole thing becomes as 1.5 minus this one comes out to be 1 by zero point 0.5, like 1 by 0.5, right? So this is 2.5 whole square, 1.5 minus 2. So if you just compute this, let me get the calculator. Um, so yeah, this comes out to be 2.5495. You can almost equate it to 2.55, right? So you have the value of impedance. Now you can calculate IRMS IRMS for the coming from the AC voltage source, right? IRMS will be equal to VRMS by Z. Now you have this is the voltage, right? This is a voltage source, this is V maximum, this 25. I've written it by mistake. So V maximum is given. Now we know that VRMS will be equal to V maximum by root 2. Sir has shown in his lecture how you get this relation, right? So it is 25 by root 2 divided by Z. Here is we have got it is 2.55 ohm. So let's calculate this. 25 divided by root 2 times 2.55. This comes out to be 6.93. Okay, 9324. Now you have that from coming from the AC source, and this is that coming from the DC source. So the total current that will be flowing through this circuit at steady state will be a contribution from both of this, and the total IRMS will be given as square root of the DC component square times IRMS square. So which is equal to IDC is 4 square plus 6.9324 square. So this will be equal to 4 square plus 6.9324 square. This comes out to be 8.003 some ampere. So this is the option is option B, 8 to 8.1. This is the correct answer. Any question in this one?
No, ma'am. Okay.
Okay, then we'll move to the next question. So in the next question, a voltage is given in the form, this is the DC part and this is the AC part. It is applied across a circuit in steady state condition and the current is given. Again, it contains a DC component and an AC component, and it is found to be flowing through it. Determine the average power in the circuit. So the power formula is still like V into I, but since we have an AC component, so the for the AC component, the power will be equal to VI cos of the angle between the voltage and the current, right? V and I, that angle theta, whatever is it. This will be the AC power coming from the AC part, and the DC part will be just simple V into I. So let us, like, since this voltage is given in cos and the current is given in sine, is as a function of sinusoidal function, so let us like convert both of them into sine so that it is easier to calculate the angle between these two. So let us write just Vt in terms of sine, or we can also write I of t in terms of cos. So Vt is equal to 20 plus 100 cos of 471 t minus pi by 6. Now if you are to convert it to this sign, we know that in this quadrant all is positive, here sign is positive, tan cos, right? So sine is positive in the second quadrant also. So 20 plus 100 sine of, we can write this as pi by 2 plus 471t minus pi by 6. Since we know cos theta is equal to sine of pi by 2 plus theta, right? So we are writing it in forms of sine. So it is 20 plus 100 sine of 471t minus, so pi by 2 minus pi by 6. So denominator we have 6. This is 3 minus 1, 2 pi by 6. So the final equation is 20 plus 100 sine of 471t minus pi by 3. This is the voltage equation. And the current equation is given as I of t as 10 plus 15 sine of 471t plus pi by 8. Right? Sorry, of course this will be plus because this will be 3 minus 1, right? 3 minus 1, 2. So yeah, this is plus. So now let us compute the total power average. Average power will be equal to the AC and the DC part, right? It is V into I, both DC plus this is the maximum, like for the RMS part, this is IM, right? And this is VM. This is VDC and this is IDC. Now, so here it will be RMS, right? So instead of that, we'll just write I maximum by root 2. So it is Vm by root 2, Im by root 2 times cos of the angle between voltage and current. So you have VDC as 20 volt, IDC is 10 plus maximum value of voltage is 100 by root 2. For current it is 15. 15 by root 2 cos of so voltage is the angle, the phase angle of voltage is pi by 3, and that for the current is pi by 8. So it comes out to be 200 plus 1500 times root 2 is 2 cos of, this is 24 pi, 8 minus 3 is 5, right? So 200 plus 750 cos of, let us just calculate this. So 5 divided by 24 into 180. So this is cos of 37.5 degrees. So cos 37.5 into 750 plus 200. So it is 795.01. This will be in watts. So the correct option is option A, which is in between these two. Clear on this one?
Hello, ma'am. 1500 divided by 2,
Yeah.
it's 750. Okay, okay, ma'am.
Yeah, this is 750. Okay. So we'll move to the next question then. Everything is fine, right?
Ma'am, in exam, calculator is allowed?
Mm, so see, if equation either like calculator will be allowed, or the value like cos 37, this is not known to people. So
Mm-hmm.
during you will be given a like standard value, suppose cos 45, that you would know, right?
Right, ma'am.
Like it will be either of the two, like,
Okay.
yeah, you'll be informed about the rules. So yeah, this is fine, right? Or do you have any question?
No, ma'am.
Okay, then we'll move to the next one. So here, the total power dissipated in the circuit is given as 25 kilowatt when the voltmeter reading across the load is 250 volt RMS. Determine R and XC of the load. So this part is the load, as shown here. This is the load circuit, and the voltage across this load circuit is given by 250 volt. Now it is said that 25 kilowatt power is dissipated in the total circuit. Total circuit would include this resistor and this particular resistor, right? So the total, like the total power dissipated will be the one dissipated by this 2 ohm resistor and this R, whose value is unknown. So as the current here is given as 12 ampere and 3 ampere current is flowing in this particular branch, the rest of the current will be flowing through this branch, and since like on applying node analysis, we will get that here again the current will be 12 ampere, right? Since this 12 ampere is entering this node, 3 ampere is flowing, the rest of the current is flowing, and finally out of this node 12 ampere current is flowing, which will flow through this particular load. So the current flowing through this load will be 12 ampere. So when we know the current across this branch, and we have the resistance, and we have the total power that is dissipated, we can calculate the value of R, right? So power is I square R, which is given by here this 2 ohm resistance into the current flowing through it is 3 ampere I square, plus here the resistance is unknown, so it is R, and the current flowing through this is 12 ampere, so 12 square, and this is given as 2.5 kilowatt, right? So 12 square is 144, R is equal to 2500 minus 9 into 2, 18. So you can calculate R. R is 2500 minus 18 is 2482 by 144. So this is 17.23. 17.236 ohm. Now among the option you can see this will be the only correct option, but we also have to calculate XC and verify whether this is coming or not. So for XC what you can do is, like, now that you know the resistance, this unknown resistance which was there before, you know this value, and you also know the total voltage drop across this branch, like from the load branch. So since, like, if we equate the voltage with the measured voltage, we can calculate XC, right? So the total voltage which is given as 250 will be equal to the voltage drop, like, since the magnitude of the voltage is given, so it will be magnitude of the voltage drop across the resistance. So this is 250 volt RMS. Remember the word RMS. So root mean square is this one square plus VC square, right? So VR square, magnitude of VR square plus VC square equal to 250 square. Like in this kind of problem, it's very easy to miss out small information like the word RMS, and we end up, equating in a wrong way. So remember, root mean square value is given. So now we have the value of R now, right? R is 17.236, or let's just get it at 17.24. 17.24 I into R. I is 12 because 12 ampere current was flowing through this, right? So let us just keep it as VC equal to 250 into 250. So VC square is 250 into 250 square minus, sorry, this one's square. Okay, so minus 17.24 into 12 whole square. So this comes out to be 19700.66. So VC will be equal to square root of this. So square root of this is 140.36. Now VC will be equal to the current flowing through it times the capacitance. So here we have to find XC, right? The capacitance, not the the total, like, you don't have to find the value of the capacitor, just the capacitance. So 140.36. Now IC is same as whatever the current that is flowing in this particular branch, which is equal to 12. So XC is equal to 140.36 by 12. So it comes out to be 11.69 or 11.7 ohm. So of course this option B is correct, which is given as R is this much, X is this much. This is okay with you?
Yes, ma'am.
Okay. Then let's move to the next problem. Here in this circuit, we have to calculate the value of C such that the current Is and Vs will be in phase. So the trick here too is to understand what does this mean, right? So when does the current and the voltage are in phase in case of a RLC circuit? So like you just know, right? Like in case of a resistance, the voltage and the current will be in phase with each other. But if there is an inductor in the circuit, in case of when an inductor is connected to the circuit, so if like if this is the current phasor, the voltage phasor will lead by 90 degree. This is only for a pure inductor circuit, right? Voltage will lead the current by 90 degree. In case of pure capacitor, so the current will lead the voltage by an angle of 90 degree, right? But whenever there is a combination of uh, R plus C or R plus L, so there will be some angle in between this, and in this case, like whenever all the three elements are present, so it will depend on the magnitude of the capacitance and the inductance to determine where the phasor lies. So it will be, if like suppose this is I, it will be either here or here depending on which magnitude is more, the value of the capacitance, or like if XC or XL is greater or less, it will depend on that. Now, can you tell me, in a like in case of only singly resistive circuit, the current and the voltage phasor are in phase with each other. But in case of an RLC circuit also, under certain condition, the current and the voltage will be in phase. Could you tell me like what could be it? Like you have been talked about this in the lectures, I'm guessing. Could you comment? Uh, Sharad, do you remember?
What, ma'am?
So under what condition the current and the voltage in an RLC circuit which has both RL and C component, they are in
Yeah.
phase with each other?
When the circuit is resistive only.
Only resistive, right? So basically,
Yeah.
in case of a combination of all this Z, which will be like a combination of all the current, resistance and inductance, the imaginary part in this particular Z has to be 0. Then only the current and the voltage phasors will be in phase with each other. So like we will calculate the Z for this branch and this branch and equate the imaginary part to 0 to satisfy this condition, so that we can calculate C, right?
Right.
Okay, so let us say this, the in this particular branch 1 and this be branch 2, this will be Z1 and Z2, the impedance of these two circuit, I mean this two branch. So Z1 is given as 4 plus J, like R plus J omega L, right? So 4 plus J, here what is the value of omega? You have the voltage source here, right? 20 cos 100 t. So omega is given by 100 because cos of omega t. So omega is given as 100. So 100, L is 40 millihenry. 40 into 10 to the power minus 3. So this is 4 plus 4j, Z1, and Z2 is given by the other branch, that is R plus 1 by j omega c, right? This is XC and this was XL. So 2 plus 1 by, so if you take j to the numerator, it will be a minus sign, right? Or like for our convenience right now, let's not put in the value of j omega c, just write it as in terms of xc. Like instead of putting the value of omega in c, we will put it at last because we have to solve this equation and it will become cumbersome. So let's just write it as, take the j on top by omega by xc. Now in this circuit, branch 1 and 2 are in parallel with each other. So the net z will be equal to z1 parallel to z2. So which is basically z1 times z2 by z1 plus z2. So we have 4 plus 4j into 2 minus, sorry, so xc is equal to 1 by j omega c, right? Sorry, it is 1 by j omega, so this will be 2 plus j into xc. So we have just taken this j to the numerator, right? So it is like, suppose if we multiply both the numerator and denominator by j, it will be, so 1 by j is equal to j into j square. J square will be minus 1, so it will be minus j. This is what we have done. So 2 minus j into xc by 4 plus 4j plus 2 minus j xc. So if we just multiply this, 8 minus 4 xc plus j into 8 minus j into j is minus 1, j square is equal to minus 1. This will like add to this, so it will be 4xc. And denominator will be 4 plus 2 6 plus j into 4 minus xc. So in order to equate this, in order to extract the imaginary part of this expression, we have to separate it out. So let us just normalize the denominator first. So I will go to a new slide. So let us just write the expression first. So right now z is equal to 8 minus 4xc j plus j into 8 plus 4xc, and denominator is 6 plus j times 4 minus xc. Okay. So in order to separate out the denominator, we will multiply the numerator and denominator by 6 minus j into 4 minus xc, 6 minus j into 4 minus xc. So we all know x plus jy into x minus jy is equal to x square plus y square, right? So let us just simplify this. Denominator will be 36, that is 6 square. 36 plus 4 minus xc whole square. On simplification of the denominator, so it is 48 minus 8, 4 minus xc minus j 4 6 4s are 24 xc. So j square plus j square equal to minus 1, so it will be minus 4 xc times 4 minus xc. Now this j plus 8, so 48j, this will be plus because there are two j's, so 8 into 4 minus xc, and the last is 24xc minus j into 4xc 4 minus xc. Okay, so since this is given as a resistive circuit, the imaginary part, we just have to get the imaginary part and equate it to 0. So let us only take out the imaginary part. So we have this j term, this j term, this j, and the last term. So it will be minus 8 into 4 minus xc minus 24 xc plus 48 and minus 4 xc times 4 minus xc by 36 plus 4 minus xc square. This is 0. So this denominator we can take it on the other side and make it to 0. So we will only have the denominator 32 plus 8xc minus 24xc plus 48 minus 16xc plus 4xc square equal to 0. So now we can solve, this is a kind of a quadratic equation, so we can solve it for xc. So it is 4xc square plus, let's see, minus 24 minus 16 is minus 40 plus 8, so it is minus 32xc. 48 minus 32 is 16 is equal to 0. So it is xc square minus 8xc plus 4 is equal to 0. So xc is equal to minus b, which is here 8, plus minus root over b square, that is 64, minus 4 into a c. C is 4, so 16 by 2. So it can be either so 64, square root of 64 minus 16, so 6.92 plus 8 divided by 2, so it is either 7.464 ohm, or it is minus of this, so 0.536 ohm. Now this is xc, so what do you have to find is capacitance. So xc is equal to 1 by omega c is equal to, let us consider the first case where it is 7.464. Now what is the value of omega? Here omega is equal to 100, right? This is in the question. So C will be equal to Xc into omega, that is 1.7.464 into 100. This comes out to be 1.339 into 10 to the power minus 3 farad, or 1.339 millifarad. So 339 can be equated to 34. So among them this has this answer. So let's calculate the other one, which is when Xc is equal to 0.536, right? So the second condition is C is equal to 1 by omega Xc 1 by 100 into 0.536. So this comes out to be 0.01865 or 18.65 millifarad. So this is actually, sorry, so, yeah. So the correct option is 1.34 millifarad or 18.67 millifarad. The correct option is D. Okay with this one?
Okay, okay.
Yeah. So let's move to the next question. In this particular circuit, it is given that at a particular frequency, the circuit below gives maximum RMS current of 5 ampere. At some other frequency, the 2 voltmeter records certain readings as shown in here. Find the voltage across R and L. All the passive elements have non-zero values. So we have to find this voltage and this voltage, provided there are two conditions given. At some random frequency, we have the voltage across the resistor and the inductor, and we have the voltage across the inductor and the capacitor given. And another condition is given that at a particular frequency, the circuit gives the maximum RMS current. So can you comment when a circuit will give the maximum RMS current? So current is given by voltage by the impedance, right? So current will increase when this will decrease. So when Z is minimum, we will get current as maximum. So when is Z minimum? When is Z like the lowest? So what is the formula of Z? Z equal to square root of R square plus XC minus XL minus XC. Mod of, like, it could be that. So mod of whole square. So as you are given, these are non-zero. So this square term is not zero, right? The only possibility could be, like, for this Z to be minimum, what could be it? This portion is equal to 0. So it is only the resistive element that is coming into play. This is negating each other out. That is, we get Z as maximum when XL equal to XC. Also sometimes known as the resonant condition. So at this resonant condition, the frequency is known as the resonant frequency, and hence in the question it is given at a particular frequency, that is at a very specific frequency. When this condition satisfies, it is called the resonant frequency. So at this, the current that we observe is maximum, which is given as 5 ampere. So this is a series, like forget the voltmeters that are connected here. This is a series circuit, right? There is a resistance, a inductance and capacitance all connected in series with a voltage supply. So the total voltage Vs will be equal to the voltage across this resistance, the inductance and the capacitance, right? So under resonance, uh, what will be the voltage? Since these two are negating each other out, voltage will be equal to current by Z or current by R, since Xc equal to XL, Z is equal to R. So current is given as 5 ampere. Sorry, I into Z. Sorry, let me just. So V is equal to I into R, right? So it is I into Z. And Z here is only resistance, so I into R. So the resistance value is given as 5 ohm. So it is 5 into the RMS value of current is 5. So 5, 25 volts. So under this condition, mod of VR square plus mod of VL minus VC all square. This is the RMS value of voltage, VRMS. And we have it as equal to 24 volt. This is RMS, so this is also RMS. So 25 equal to square root of VR square plus, now VL minus VC. So so the voltage across L and C, it is given as 22 volts, right? So at any certain frequency, the measured difference between these two voltages 22 volt. So VL minus VC will be equal to 22 square. So if you just take a square of this, 25 square minus 22 square is equal to VR square, right? So we can calculate VR square root of, so 25 square minus 22 square. So this is 141. Therefore VR is equal to square root of 141, 11.874. So in the question you are asked to calculate voltage between resistance and also inductance. So now we have the voltage across the resistance. Now we have another voltmeter which is recording the voltage between this resistance and this inductance, right? Which is given as 30 RMS. So we have VRL RMS value is equal to square root of VR square plus magnitude VL square, right? It is given as 30. And we already have VR square as 141, right? So 141 plus VL square. So VL square will be equal to 900. We just take a square of both sides minus 141. So VL is 900 minus 141 square root of it, which is 27.49 volt, 27.54 volt. So the correct option is VR is 11.87. So it lies between this range, and it is 27.54. So it lies between this range. So the correct option is option C. Is this clear to you? Uh, I hope you're getting this. Okay. So I guess no one is here. So I'll stop this for today. Um, so we will meet in the next interaction session.